Okay, Assalamu alaikum wa rahmatullahi wa barakatuh. Let's begin the lecture. Today we're gonna, inshallah, we're gonna finish chapter 4, and also we're gonna begin talking about chapter 5. Okay, as we mentioned before. As far as chapter 4, last two lectures we talked, the last two lectures we talked about the joint CDF, joint PDF, and how we derive the marginal CDFs and PDFs from the joint PDFs. And today, as I mentioned, before chapter 4, it's kind of short. So today we're gonna finish where we're gonna talk about conditional distribution function, conditional distribution and density function, and then we'll talk about independence. And all that, this is nothing new to us because we learned that in previous chapters. Okay, chapter 2, I believe. Okay, so if we go back to chapter 2, and if you just refresh your memory as far as the conditional distribution function, distribution and density function, they are given in these two equations on the screen, as you can see, where you have, this is the conditional CDF, the CDF of X given B, the event B, it's given by this equation. And of course, if you have the conditional distribution, you can find the conditional PDF or density function by taking the first derivative of the first equation. Now, in some cases, we are interested in finding the distribution of a random variable conditioned on the specific value of another random variable. So, for example, let's say if we have X and Y, so we need to find the distribution or the density function of a random of X, given that Y has a specific value, let's say small y. And this is called point conditioning, okay? This is very, very straightforward. We're not going to go through a lot of details. We're just going to go through the expressions here. So for discrete random variables, the CDF, the conditional CDF of if y has specific value y of k, this is for discrete random variable. So the conditional CDF x, x given y, where y is small y k, it will be given in this expression 3, and the PDF obviously after you take the first derivative, you will end up with the equation 4. As far as continuous, we're going to focus on the conditional PDF. So the PDF of X given Y, it will be given as the joint probability of X and Y divided by the marginal PDF of Y. Similarly, the conditional PDF of Y given X, okay, it's equal the joint PDF of X and Y divided by the marginal PDF of X. Okay, so these are the most important ones we're going to focus on. As an example here, if we recall back, from last lecture, if you go back to lecture 17, we did have a PDF and a joint PDF, that is, and we derived the marginal PDF for X and Y. So these are the main results. From there, we need to find the conditional PDF of X given Y and PDF of Y given X, just by basically applying X 5 and 6. So from here, so this is the joint PDF. Joint PDF divided by, in this case, divide by this right here, which is the marginal PDF of Y. So after you do the simple math here, you will end up with equation 10. So that would be your conditional conditional PDF of x given y, and you do the same thing for conditional y given x by taking the joint PDF here divided by x, the marginal PDF of x. So that's all I want to talk about as far as the conditional, because we talked about conditions before. So this is just applying it to joint PDFs. Similarly, as far as the independence, if you recall, we said if we have two events and those events are independent or statistically independent, then it means the probability the probability of the joint, the probability of the intersection between A and B, events A and B, is equal to the probability of A times the probability of B. So if this condition is satisfied, it means A and B are independent. So we can apply this one to the joint PDF and joint CDF. So for the joint PDF, CDF in equation 13, as you can see, it's the probability of x, x less than small xy. So we can do that. We can say the joint PDF or the joint CDF, it's equal to the CDF of x times the CDF of y. So if that's valid, so if we take the marginal CDF of x times the marginal CDF of y, and the end result equals to joint CDF, it means x and y are independent. Similarly, as far as the PDF, the joint the marginal, if you take the marginal CDF times the marginal CDF, sorry, the marginal PDF of x times the marginal PDF of y, when you multiply them by each other, if you ended up with the joint PDF of x and y, then x and y are independent. Otherwise, they are not. Okay. On equation 3, on page 3 here, again, if x and y are independent, it means after as far as the conditional probability, so let's say the conditional CDF of x given y. So after you apply this one here, because we said this is equal to the joint CDF, the joint CDF divided by the marginal CDF of y. So obviously the joint CDF here, if x and y are random variable, independent random variable, they will be written in this way. So this will cancel this one, and you will end up with the joint CDF of x given y. It's going to be the marginal CDF of x, which is obvious, because it means that x is not depending on y in this case, because they are independent. And you can do the same thing for the other one, y given x, and you do the same thing for the PDF. Okay, it's very straightforward. Okay, so let's take an example here. Let's say from the example we just learned a minute ago, we have the joint PDF, sorry, and we have the marginal PDF of x, marginal PDF of y. Okay, and now if we take these two marginal PDFs, f of x, f of y, multiplying by each other, okay, like this, and obviously the end result is not going to be equal to this joint PDF, which means in this case x and y are not independent. Okay, if they are equal, then they are independent. And the same thing, we have this example right here, example 3. We have joint PDF of x and y. Okay, and we need to determine whether x and y are independent. In order for us to do that, we need to find the marginal PDF, like we learned last lecture. You take the integration of the joint PDF with respect to, now we have unit steps here, u of x and u of y. So you do this with respect to y. That would be the marginal PDF of X, and this is the marginal PDF of Y. We do the integration like we learned last time. So these are the end results, 22 and 23. Okay. Now we have all the information we need. We have the marginal PDFs, and we have the joint PDF is already given to us. So we'll find out if we take these two marginal PDF, multiply them by each other. Okay, we will end up with the same expression right here in 21, which is the joint PDF, which means in this case X and Y are independent. Okay. So this is really the end of chapter 4, and as usual, I try to give you some suggested problems to kind of represent the chapter. So these are the problems that I think if you try to solve them yourself, and if you feel like you need to solve more, that'll be better, of course, and you try to do all the examples in the book so you can understand it. Okay. So as I just mentioned, or as I mentioned at the beginning of the lecture, we finished chapter 4, and we're going to jump to chapter 5. Now, chapter 5, it's talking about operations on multiple random variables. If you recall, in chapter 3, we talked about operations after we introduced the PDF and CDF. We introduced the PDF and CDF in chapter 2. In chapter 3, we went through some operations, which is the expected value, the moments, and things like that, if you remember that. Okay, so similarly, we're going to do this here on, on the two random variables, X and Y. So the first thing we're going to briefly talk about expected value of a function of random variables, where the function is a function of X and Y together, okay, G. And of course, if we have a function, we did that actually back in chapter 3. So this equation is very similar to what we talked about expectation chapter 3. The only thing here we have in there, we had the PDF. In here we have joint PDF, X and Y. And this is the function. There kind of we dealt with the function of X or a function of Y by itself. In here we have a function of X and Y together. So obviously we have to do the integration for X and for Y as well. So double integration. Okay. So this is the expected value, which is or the mean of both random variables X and Y. And similarly, this is for discrete random variable. Okay. Now, as far as moments, okay, if you recall, we talked about moments there. It's the same thing in there in chapter 3 when we had a single random variable. Obviously, Y was not there, and we had a single PDF, the PDF for X, for example. In here, we added Y, which is the second random variable. So we have the joint moment is going to be we denote the joint moment by M subscript N and K, where N is the moments for X and K the moments for Y. So of course here we do the integration. Like I said, this is the main equation, of course. And so you can, of course, here, like I said here, if N is equal 0, if K is equal 0, we'll end up with the moments of K, moment of X. So if this one is equal 0, K, this one will go away, will be 1, of course. And once we do the integration, we'll end up with what? We'll end up with the moments of X, because the integration of the joint PDF of Y, the part Y will be 1, of course. Okay. The same thing. If you want to find the moments of Y from the joint moment, you will set N2 equal to 0. Okay. Another thing we need to keep in mind: the sum of N plus K, these two parameters right here, n plus k, is the order of the moments. The order of the moments. So in this chapter or this semester, we're going to deal with two moments, the first moment and the second. Well, in chapter 3, we focus on the first moment and the second moment. In here, we're going to focus again on the first order moment and the second order moment. That's all. So for example here, 0, 2, 2, 0, and 1, 1. So these moments, okay, 0, 2 حكينا إنه إيش؟ they're all called second moment, okay? And 0, 1, 1, 0, all these إيش? First moment, the first order moment. So the first order moment, basically, it's the mean, okay? The mean of either x or y. So the first order moment, either 0, 1 or 1, 0, that would be the expected value of x or y. But the second order moment, which is either 0, 2, 2, 0, or 1, 1. So if you set k to 1 and n to 1, and you do the integration, you end up with second order moment. So now, the second order moment, 1, 1, this one, it's called correlation of x and y. So the correlation of x and y, basically the second order moment where n is equal 1 and k is equal 1. It's not 0, 1 or 1, 0. It's not 0, 2 or 2, 0. It's 1, 1, both of them, okay? And how you find this, of course, like, by going using this this expression in equation 3, where you set n to 1 and k to 1, and you do the integration. So this is basically the correlation. How we find the correlation, and we're going to refer to it. The correlation between x and y, it's r subscript x and y, which is the expected value of x and y together, multiplied by each other. Now, if x and y are independent, then the correlation can be written in this form, where you take the expected value of x times the expected value of y. If x and y are independent, it means we can write the expected value of x times the expected value of y, and in this case we call in this case these x and y are said to be uncorrelated. Okay, so if they are independent, if x and y are independent, it means x and y are uncorrelated. Okay. Now, if the correlation is 0, okay, if the correlation is 0, it means x and y said to be orthogonal. Orthogonal, like the angle between x and y is 90 degrees. So let's take this example to clarify what we just talked about. Let's say we have x. It's a random variable that has the mean value, it's equal 3, and the variance of x is equal 2. Okay. Is equal to, and then we can take the second moment of this one. So from there we can find the second moment. Of course, the mean is equal. We learned that from chapter 3. So if we have the variance is equal to the second moment of x minus the mean squared. So we already have the mean here, and we already have the variance. Okay. From there, what we can find the mean, the second moment of x. Okay, just straightforward derivation. Okay, and let's assume that we have a random variable y. It's another random variable in terms of x. Okay, a random variable y, where y is equal minus 6x plus 22. It's in terms of x, which means we can find the expected value of y, okay, which is going to be the expected value of this expression minus 6x plus 22, okay, and obviously we learned from chapter 3 that we can break this one in this form, which is going to be minus 6x bar, which is the mean of x, plus 22. which means that the expected value of y in this case is equal 4. Okay. Now we need to find the correlation between x and y. The correlation between x and y is, it's basically x times y, the expected value of x times y. So we already have, we don't have to do an integration, because all we have to do is just take x times y, which is, this is expression in terms of x as well. So after you multiply x by this expression, you will end up with the expected value minus 6 squared plus 22x. And we can break this one as shown in equation 7. It's going to be minus 6 times the second moment of x minus 22 x bar. And we already found, if you go back here, we already found the second moment of x by using the variance and the mean. So we plug in the numbers and we would end up with Rx is equal 0, Rxy, which is the correlation. It means by doing all these numbers, we found that the correlation between x and y is 0, which means x and y are orthogonal. Okay. Now, if we multiply the expected value of x times the expected value of y is equal 12. Okay. Is equal 12. Okay. Which, of course, if it's equal to 12, it's not equal to 0, which means x and y are not independent either and not correlated. Okay. And which is obvious. Okay. Because this is 0 and this is 12. And since you multiply the expectations by each other, we ended up with a number different than 0. Obviously, they are independent. They are not independent, and as a result, they are not correlated as well. They are not correlated as well. Now, in here, we talked about the moment about the origin. If you remember, if you go back to chapter 3, we talked about the moment about the origin, and also we talked about the central moment, where the central moment, where x, the random variable x at that time was shifted by the mean of x, shifted to the right, that is. So in this case here, the moment denoted by mu. So for the joint central moment, we can refer to it as mu. Now for the moment at the origin, it's going to be small m, okay, subscript x and y. In here, we're going to call it mu, okay. And you do the same thing. The only difference is, do the integration. The only difference is x and y, they are shifted by their means to the right, okay. And the second order central moment, again, for when mu, when k is equal 0, we will end up with the variance for x, and when n is equal 0, we'll end up with the variance of y. Okay. Now the second order joint moment, mu 1 is very it's called covariance. Now if you go back here, m's 1 we called it what, correlation, but here the second order joint moment, the second order moment, it's called covariance. Okay, and we're going to refer to it C, capital C, subscript x and y. Some books they refer to it as COV, cove. You know, both of them are okay. So if you see it in our book or other books, cove, it's the same thing as capital C, x and y. Okay, and of course the covariance is equal to the expected value of x shifted by its mean times y shifted by its mean. Now we can multiply them by each other and break them by using this identity right here. And after you do that, the covariance will be equal to what? Equal to the correlation of x and y minus the mean of x times y, minus the mean of x times the mean of y, as you can see here. Okay. And another important identity we need to talk about is the correlation coefficient of two random variables. Correlation coefficient. Okay, and it will identify how correlated. So the correlation coefficient is between -1 and 1. So two x and y are correlated. If it's close to 1, it means they are going very close together all the way up, positive. If it's close to negative, they are going down, decreasing together. If it's 0, it means there is no correlation. Okay. And how we find the correlation coefficient? By first you need to find the covariance, which is right here, and you divide it by the variance of x and y. Okay. Now, if the covariance is 0, it means x and y are independent and uncorrelated. Why? Because by looking at this, take a look at this. Of course, the correlation, it's the expected value of x and y. Now, if x and y independent, this we can break it into the expected value of x times the expected value of y, right? Then obviously after you do the math, you would end up with 0, which means obviously it's independent. Now, if the correlation or if the covariance is not 0, which is something like this, okay, it's given by equation 4 minus the expected value of x times the expected value of y, it means x and y are orthogonal, okay? If it's orthogonal, it means, you know, if it's given in this expression right here, it means the correlation is 0. As a result, x and y are orthogonal. And I think that's enough. We had a lot of information here today. Of course, chapter 4, we had a couple of information talking about conditional joint CDF and PDF. And also we talked about independence. That was not really a big deal. Okay, and in chapter 5 here, we talked about expectation. Also, even though expectation and moments are not new to us because we covered that in chapter 3. The only thing new is talking about more correlation and covariance and correlation and correlated and things like that. So I'm not going to go beyond this point here. I want to give you a chance to try to digest this information, try to do some examples, understand it, and then we can finish, inshallah, continue with this topic on Sunday, next Sunday. Okay? You guys have any questions about today's lectures?
دكتور لو سمحت.
تفضلي.
بصير ترفع لنا أسئلة practice problem على e-learning؟
نعم.
بصير ترفع لنا أسئلة practice problem على e-learning؟
البراكتس problems؟
نعم.
موجودات مش موجودات تمو؟
ما شفت صراحة.
دقيقة شوي. هذول اللي ورجيتهم هلا قبل شوي، هذول اللي بتحكي عنهم؟
نعم، بس لأنه الكتاب كمان ما بعرف أي نسخة وهيك.
أنا الكتاب، أنت بتحكي عن الكتاب نفسه. أنا الكتاب موجود على في الكتاب موجود والسولوشن موجود. أوكي؟
تمام دكتور.
موجودات على النت. يعني أنا بالبداية حكيت لكم إذا الكتاب مش موجود بدك تدوري عليه على النت. أوكي؟ أنا بس بعطيكم الأرقام. أنا وحتى السولوشن لهذا السبب بالبداية حكيت لكم إنه اللي معهوش نسخة يسأل زملائه، ممكن ناس عندهم نسخة والسولوشن موجود، بس الأفضل إنه الواحد يحاول يحل بالبداية قد ما يقدر، وبعدين يتأكد من شغله قبل ما يطلع السولوشن للمادة هاي ولكل المواد طبعا. أوكي؟
نعم دكتور صح.
أوكي.
شكرا.
فاسألي زملائك أو أنت، يعني you can search for it. طبعا أنت معك السيلبس ولا لا؟
نعم معي دكتور.
بتقدر يعني انت تعمل سيرش فور، بتقدر تلاقي الكتاب نفسه وبتلاقي السولوشن، او اسال زملائك ممكن يقدروا يساعدوك بالحاله هاي. اوكي any questions بالنسبه لليوم ولا كل شيء تمام؟ اوكي if you don't have any questions يعطيكم الف عافيه and I will talk to you ان شاء الله on Sunday. يلا السلام عليكم.
يعطيك العافيه دكتور.
الله يعافيك، شكرا.